from the Sham book. Okay, so these are from chapter 6. We're solving these as linear DEs. This one's also separable. I could solve it that way. In fact, like maybe I'll do this one both ways. It's also exact. We could solve it as an exact DE, isn't it? Let me think. Yeah. No, it may not be exact in this form. Anyways, my point is there are multiple ways to solve it. Let's solve it as a linear DE. So linear DEs have y prime, y double prime. Every version of y can only be to the first power. Can't have any signs of y, can't have exponentials, can't have logs of y, nothing nonlinear in y. This is linear. We've got y prime to the first power. We've got some function of x here. Your book likes to call that p of x times y to the first equals 0. And that p of x here is 2x. I don't care about this part. That doesn't have to be linear in x. That can be anything. Over here, we could have anything in x. To be linear, we need all versions of y to be to the first power. Okay, this one we can solve using an integrating factor. So our integrating factor, the Sham outline likes to call that capital I of x. I prefer to call it mu, since that's what the homework tends to call it. Mu of x is e raised to the antiderivative of p dx. So that would be e raised to the antiderivative of 2x dx. If you don't put that dx right there, there's a point off. You will never write an integral without writing a differential. Antiderivative of 2x dx is x squared, so that's e to the x squared. Technically plus c, but when the integrating factor, we don't include the plus c. So don't put a plus c here. That's what we're going to multiply everything by. So I multiply everything in the DE by the integrating factor. Zero, I'm going to write it here, but 0 times anything is 0. Then if you've done your math right, the left-hand side should be the product rule derivative of your integrating factor times y. And we should check that. So the product rule derivative, remember y is a function of x. So I've got two functions multiplied here. The derivative of e to the x squared times y would be derivative of the first. That's chain rule. Derivative of e to the anything is e to the same thing times the derivative of the top times leave the second one alone plus leave the first one alone times the derivative of the second. What's the derivative of y? Y prime. So that's it. If I were to take the product rule of these two guys, I would get the left-hand side. If that doesn't happen, you've done goofed over here somewhere. Okay, so that means the left-hand side is somebody's derivative. I can integrate both sides. Right here at this moment is where mistakes happen. The next step, you have to write this. Take the integral of both sides. And here's what people like to write. That would be a -2 right there. I've written this symbol and I did not write a differential to go with it. I have to put a dx right here. Same thing over here. You have to write those. Otherwise, you're writing mathematical nonsense. Then the antiderivative of the derivative, those are inverse operations. These just cancel out. You just get what's inside. E to the x, oh, that's an x squared, sorry. E to the x squared y. Sorry, there's a chat. I didn't add any. Have you? Maybe you haven't watched the lecture videos yet. This is the process. This is how we solve linear DEs. The integrating factor is e raised to the antiderivative of p dx. The antiderivative of 0 is c. And there's implicit form. We could just stop there. Or, but by the way, right there, that's when we get the c. When we actually integrate both sides, that's when we throw in the c. Now we want to solve that for y. So we want to divide this guy over, or so I could think of this as c over e to the x squared, or multiply both sides by the same thing with a negative exponent. That's c e to the negative x squared. These mean the same thing. Okay, we could also have solved that one as a separable DE. Probably would have been less work. So I had, let's see, I had y prime equals negative 2xy. If I move that guy right there to the other side, get all the y's on the left side. So dy over y equals negative 2x dx. Remember, that guy is dy dx. So I've kind of multiplied the dx up. Integrate both sides. Both sides already has a differential. Antiderivative of 1 over y is natural log the absolute value of y. Antiderivative of negative 2x is, let's see, negative x squared plus c. And then use rules of exponents to say, oh, well, I'm going to make both sides powers of c. Again, we're taking our positive branch, so we won't have to worry about that absolute value. We do that all the time. And we get e to the negative x squared times e to the c. And then we're just going to call that thing some new c. Oh, look, that's the same thing we got here.
For the test, Professor, obviously, will it be open to our interpretation of which method to use, or will you specify what you would prefer?
No, the only ones you kind of have to do one way are exact DEs because it's the only way that'll work. But something like this, no, you could do either way. You would get credit. Either one of these would get you full credit.
Okay, and also, there was a problem similar that I kind of got stuck at, where I got to where you raised the equation to the power of e for the natural log of y, but on that left-hand side of the equation, there was also just a y added.
Yeah, that was the that last group assignment. You're just stuck. You can't do it.
Yeah, that's where I'm stuck at.
Yeah, no, you're done. That's the answer. You could sometimes implicit form is the best you can do.
Okay, and then you just go ahead and solve for c from that point where you're stuck at?
Yep.
Okay, great. Thank you.
Yeah, because you get something. He's talking about the group assignment. And like, don't quote me on this, but you get something that's kind of like this equals, I don't know, x plus c, something that looks like that. You plug in here your initial conditions, and I don't know, I think you get c equals 7 or something like that, some version of 7. So then your final answer is just going to look like this. And you do still have the absolute value. And maybe it's -7. But like, this is what you will circle. It'd be something like that. It's impossible to solve that explicitly.
Yeah, that's what I figured I was stuck for a reason. And also for the exam, is implicit form always going to be acceptable?
You'll always be able to tell by the way the question is asking. If the question will specify. If it says y equals and there's a box, you have to solve it explicitly.
Okay.
But like on exact DEs, we're solving for some function of x and y equals c. And it will say, just like in the homework, exactly like in the homework, there'll be a box and it'll be asking for that F. And then there you'll have some implicit form. You won't even have an equation. You won't even have the equal C. You'll just be typing in the F. Okay, so it's very similar to what we're doing in the homework. In fact, a lot of the questions come from the homework or are variations of homework problems. Okay, let's do another one. Again, this one's also separable. We could solve it separable. We could solve it as linear. The thing in front of y right there is my p of x. My integrating factor. Everything you're seeing me write is required for a full solution, by the way. Mu. Let me make my mu's look more like mu's and less like m's. I guess that's a little better. Mu of x is e to the antiderivative of 3x squared dx. Antiderivative of 3x squared is x cubed. That's what we're going to multiply everybody by. Order doesn't matter here. Like where I put this guy in this term here, it doesn't matter because multiplication is commutative. Okay, then we should check that the left-hand side is the derivative of, and it's always the same thing, the integrating factor, that thing you got right there, times y. So you want to go through, take the derivative of this and check. Derivative of the first is that stuff right there. That's the derivative of e to the x cubed times leave the second alone plus leave the first alone times the derivative of the second. So it's right. The left-hand side is that derivative. Then we integrate both sides. Don't forget right here, again, number one place people miss points on test one. They forget to write this dx or dt, whatever we have right there. Right there, that spot right there is where it happens. The integral and the antiderivative, or the antiderivative and the derivative cancel out. We get e to the x cubed y. On the right side, antiderivative of 0 is just c. And then again, look, it's almost the same problem as before. I could write that as c over e to the x cubed. Or c e to the negative x cubed. Either of those is fine. Okay, let's do a couple that are a little more complicated where we, like here, we actually got something on the other side. Okay, so my p of x is x squared. So my integrating factor, mu of x, is e to the antiderivative of x squared dx. That would be e to the x cubed over 3. Yeah. All right. Multiply everything, both sides by that. Okay, then check and make sure that the left-hand side is the product rule derivative of y times the integrating factor. And it is, because the derivative of that junk right there is e to the same thing times the derivative of the exponent. Derivative of x cubed over 3 is x squared. Okay, here's where we're going to run into issues on this problem. Now we take the antiderivative of both sides. Don't forget your dx right here and here. Left side is easy. It's always the same thing, always. A lot of times people like to skip this step. They don't write this step down and they jump straight to here. And mathematically, that's true. You can mathematically jump straight to this step because it's always going to be the same thing. Like you could mathematically, it's true, you always go to here. I still want to see this step. I want to make sure you understand the math in the background. The Sham outline, after they do a couple of examples, sometimes they skip this step here. They just jump straight down to here. And maybe that's why people do it on tests. I want to see that step. That's a required step right there. Okay, here's where we might have issues. What if we don't know how to do this one? I could easily make up a problem where this antiderivative is undoable. If that was a 1 right there, instead of an x squared, if this right side were just 1, this guy here would have no antiderivative in elementary form. So just because something's linear doesn't mean we can do the problem. So you got to always keep that in mind. You might get here and be like, well, crap, I don't know how to do that. So this didn't help. In this case, it did. We can do that, but only because this was picked very specifically to give us a substitution over here. If that were x to the first instead of x squared, I would have no idea how to do this antiderivative. In fact, there probably would not be an antiderivative in elementary form. You probably have to use power series to do it. Okay, but we can do this. We could say u equals x cubed over 3. Then du is x squared dx. So we could rewrite this. Here's my e to the u. And these two guys right there make up my du. Antiderivative of e to the u du is e to the u. But I know what u is. It's x cubed over 3 plus c. So we get this. It's important, I know I keep saying this as well, that the plus c pops up when you do the integral. You can't wait until the end and just go, okay, at the very end, I'm going to tack a c someplace. That c, I guess I should put it here too then. That c comes right there when you do the antiderivative. Okay. Now, if I want to write this in explicit form, I need to get rid of this guy right there. So multiply everything. Here, I'll even write out the step. Multiply both sides by e to the negative x cubed over 3. So that'll cancel over here. That'll cancel this guy, leaving a 1. And then c times that. Okay. Now, I've mentioned a couple of times that it's okay to check your answers, that I want you to check your answers. Let's do that. Let's check this. So my DE was y prime plus x squared y equals x squared, I think. Let me check and make sure that was right. Yeah. Check and make sure we typed it in right. Look, there's the answer. That's perfectly fine on a test. In fact, I want you to check your answer. That's okay. Notice I haven't copied anything. I did the work first, then I went and checked it. And maybe if I goof somewhere, I could look at that and go, oh, I must have goofed. Let me go back and find my mistake. That's fine. What's cheating is hitting this button right here, hitting the GoPro, paying for something, and copying down their work. That's cheating. If you're paying for anything, you're cheating. And you guys know that. Look, I don't really have to. I guess I do because I catch people every semester, but I shouldn't have to say that. All right, I think I got one more picked out. Yeah, I figured we'll do an IVP. Okay. These problems, I think, are really interesting. These ones that look like this, it's some number over X. So you got a lot of homework problems, a lot in the Sham book that look just like this. They just have a different number right there. That number right there, that 2, is actually the most important thing in the problem. You would think that if I change that to a 4, it wouldn't really change the problem much. It would. It would change it completely. The 2 is the most important number there. I just find that kind of cool. All right, so here my P of X is 2 over X. So mu, my integrating factor, is e to the antiderivative of 2 over X dx. That would be e to the 2 natural log absolute value of X. And again, we're going to assume, always assume, anytime you get an absolute value, assume X is positive so you can drop the absolute value. In this case, it wouldn't matter because I've got a 2, which would square us anyways. So like literally, I don't have to worry about that here because this 2 comes inside rules of exponents, rules of logs. That would be X squared. X squared is always positive. I don't need to worry about the absolute value anymore. E raised to the log of anything is that thing. So the E and the log cancel out. So if that had been a 4, I would have ended up with X to the 4th. If that had been a -7 right there, I would have gotten X to the -7. Whatever number is right there is going to end up being your power on X in your integrating factor. That's what I multiply everybody by. X times X squared would be X cubed. So multiply everything by the integrating factor, both sides. And here we get a little cleanup. One of those X's cancels. I just get 2xy. Then if I've done everything right, the left-hand side, I should be able to like undifferentiate that, unproduct rule that, and say, well, that's just y times this guy. Always y times this guy. And you should check and make sure. So derivative of y times, leave the second one alone, plus leave the first one alone, times the derivative of the second. It worked. Take the antiderivative of both sides. Don't forget the dx on both sides. Left side, we just get what's inside, yx squared. On the right side, antiderivative of x cubed would be what? X to the 4th over 4 plus c. You got to put the plus c in there. And then let's multiply everybody here by x to the -2. Or divide by x squared. So we could write this as x squared over 4 plus c, x to the -2. Or I guess I could write that as x squared over 4 plus c over x squared. Either one of those is fine. And then this is an IVP, y of 1 equals 0. So let's solve for c. So remember, that's an x. That's y. So what do we get? 0 equals 1/4 plus c. So c equals -1/4. So then my solution, I've noticed on the group assignments, sometimes when you're asked to solve an IVP, people want to stop right here. They think, I got C, I'm done. You're done with the hard part, but you haven't answered the question yet. The question isn't solve for C. The question is, what's the solution to the DE? You got to go through this last step, write out the DE, the solution. And again, we can check this answer. Is that here in Wolfram Alpha? Let's see, that was y prime plus 2 over xy equals, I've already forgotten, x, y of 1 equals 0. So I just put a comma, y of 1 equals 0. Oh, it got confused there. Normally it's pretty good with order of operations. Look, it thought I meant I wanted that y in the bottom. See, that's why it's good to check and make sure it interpreted what you typed wrote correctly. Now it's correct. And look, that's the same thing we got. We got x to the 4th over 4. Is that what I got? X to the 4th over 4 minus 1/4 over x squared. Same thing I got. Again, check your answers on the test. I mean, how long did that take me to come here and type that in? No time at all. That's completely different than talking to your buddy that took this class last semester. That happens every semester too. Somebody said, well, my roommate did sit and kind of help me with the test. Yeah, well, I'm sorry, I got to give you an F in the course. That's cheating.
I have a question.
Yeah.
So like the homework assignments from yesterday and the week before, like during the exam, will we still have access to those homework assignments? Because like there's like videos in there.
If you're relying on watching YouTube videos in the middle of a test, you're not going to do well on the test. Yes, you do still have access to it. You don't have time to sit through a whole bunch of YouTube videos and scroll through homework problems trying to find similar problems. You don't have time for that. So yeah, to answer your question, you'll still have access to it, but don't go in with that mindset.
I understand. I was just asking.
Yeah. Okay, any other questions? Concerns, anything at all?
So do you prefer the method you've been using over treating it as a separable DE?
No, I don't. Honestly, if you give me a DE, separable is the first thing I always look for.
Yeah, that's where my brain is going. So I was wondering why you're always showing this way.
Yeah, but like this one here, this is not separable. That would not work with this one.
Excuse me, Professor.
Yeah.
Are your tests like the homework or like exactly basically what you give in class?
Did you come in late?
Yes, about like 10 minutes.
Okay, make sure you go back and rewatch the beginning then, because yeah, I talked about that. It's a lot like the homework.
Okay, then that's no problem.
Yeah.
The homework is pretty fair, I'm not gonna lie.
Yeah. Yeah, I don't have a huge wealth of problems to pick from. Like, it's not like I have 1,000 linear DEs to pick from to put on the test. I've got more like, I don't know, maybe 40, something like that. So a lot of the good ones I already used for the homework. So you might, honestly, you might only have 3 or 4 questions in the homework or in the test that weren't already homework questions. I reuse a lot of questions is what I'm saying. That there will be different numbers. Like, even if you go back and redo the homework again for practice, you'll get slightly different problems. Like I mentioned before, if I change that 2 right there, if I change that to a 3, this becomes a completely different problem. So even though it might be under the same homework problem, a lot of the process is going to be different. Does that make sense?
Yes, sir. Thank you.
Uh-huh.
So what are you like quickly like scanning for to tell you that you couldn't end up you treating that as separate?
There, I can see right here, there's no way to get this Y isolated from that X. So here, let's say we tried to separate it. So I've got dy dx. I'm going to move this stuff to the other side. -2 over xy plus x. There's no way I could, you're only allowed, when you're trying to separate variables, you get your y's together through multiplying and dividing, not through adding and subtracting. Because I have to multiply this side by dx, right? I have to do this. There's no way I can get that y out of there away from that dx. Those are multiplied, and adding it back over here won't do any good. If I left it like this, if I did dy over dx plus 2 over xy equals x, and now I multiplied everything by dx, I would end up with something weird like this. So now I've got dx's on both sides of the equation. There's a plus there. There's no way to get those two away from each other.
I see.
If we had a slightly different problem, if I had this problem instead, 2xy equals x. See how that x is being, instead of being in the bottom, if I put it in the top, I would actually be able to separate this. So let me show you how that would work. This one's going to be a little trickier. So I want a minus there. Sorry. So I move this to the other side. I've got a common factor of x now that I could factor out. See, now that's something I can divide over. This whole quantity here, you can only move your y's to get them with the dy by multiplying and dividing. Adding and subtracting a y over ain't going to help. But this now I could do dy over 1 minus 2y, excuse me, equals x dx. That could be solved. In fact, you had a couple homework questions where you had to do this. You're going to have a test question. I can pretty much guarantee you're going to have a test question where you got to play a game like this.
With the factoring.
Yeah. Factoring out that common factor to get rid of all the x's here so you can divide over and get just y's on the left, x's on the right.
I don't want to end up wasting a bunch of time trying to treat it as separable and then it end up being I can't. So I was wondering,
Yeah.
how you quickly assess it.
Yeah, it's just from experience. Honestly, that's the best I can give you. Is some of them are obvious. I think, like, I thought these were obviously separable up here because I can see if I move that over, I can divide the y over, similarly to what I did here.
Yeah, and it seems like a lot of the problems are always ending in like the natural log of y. Is that just by chance, or do you kind of design them that way?
Right. Okay, I'm gonna give you the lowdown on this class. In the real world, if you write down a differential equation for a real world problem, 99.99% of the time, you have no way of actually solving that DE. You have to solve it using some numerical method in the real world. All these techniques we're learning are for only specialized cases. That's why I told you there aren't that many linear DEs from my pool that I can pull from. That's because it's really hard to write one that actually is something you guys could figure out. So most of these problems are set up, and like, I guess the way I'm answering your question is, in order to set these up so that they're doable, that's one of the things that ends up happening, is like dividing by that y. That's one of the easier ones to set up.
Okay, I see.
Yeah, like here, as a non-example, I want to erase all that stuff I did just a minute ago first. I didn't want to go this long today, but I kind of want to go a little further with your question. Here's a non-example. I see there's a chat. I'll check it in just a minute. Let's say we had like here, looks like a pretty simple DE. It's not that complicated. My integrating factor is the antiderivative, or sorry, e to the antiderivative of 2x dx. That's e to the x squared. I tried to make up a non-example, and then I picked one that's actually really easy. Hold on, I got to fix that. This one would be easy. What I meant here was just x to the 5th. Or even 1. Hell, let's do that. That's even an easier DE. That looks incredibly simple. Multiply everything by e to the x squared. Here. Integrate, well, here, I don't want to skip this step. Left side is the derivative of y e to the x squared. Integrate both sides dx. Left side's easy. Left side's always easy. That's y e to the x squared. The right side, this is a well-known antiderivative that does not have an elementary antiderivative. It doesn't, you can't do it. It's impossible to find this antiderivative and write it down in a finite number of steps. This is sometimes called the error function, this antiderivative. Like you should have seen that in Calc 2, that there's no way to take this antiderivative. We write it down using power series, which goes on forever. So all these problems that we have in homework that I'm doing examples of, they're set up so that there's something, once you get down to this step here, it's something you can actually do.